I am Hyodok Shin. I'm a faculty at Rady School of Management at UC San Diego. This symposium, we have great discussions, student presentations, as well as panel discussions on the future of autonomous transportations and electric vehicles. And with that, we will start with our welcome remark. Let's start with An Amil. An is an associate dean at Rady School of Management. He is also a Wolf Family Presidential Endowed Chair in Life Sciences, Innovation, and Entrepreneurship. An has done research in psychological and economic principles to identify successful strategies in various markets. With that, An.
Thank you, Shin. Welcome everyone to another exciting symposium that Shin organizes. Shin and Company organizes. These are amazing. If you look at the list of panelists and participants, it seems like you don't want to be anywhere else. But let me just, as a background, why this is so great. So the Rady School of Management was established in a research university, in the major research university in Southern California. And it was established in order to make the connection between research and business. And the motto, if you will, of the Rady School of Management is the science of business. And this symposium is such a nice connection between ongoing research in many domains and its application in the marketplace. And so it's a really good fit with what we do here at the school. And I'm very, very excited to hear what everybody has to say. And I welcome everyone to the beginning of what looks to be a great day. Thank you, Shin. And thanks everyone, panelists and participants.
Great. Thank you, An, for the great welcome remark. And before we begin, I would like to introduce actually our institute who is organizing this symposium. This is initiated by the Institute for Supply Chain Excellence and Innovation at Rady School. And in our Supply Chain Institute, our key focus is actually looking at the supply chain of the future. And when we look at the supply chain of the future, we have done some research in the past. The first one was actually about the post-globalization movement. And this symposium is actually a part 3 of the post-globalization movement. And with that, what we identified is a regionalization of the supply chains instead of the globalization. And that is one pillar of our institute, which is look at the supply chain in a more regional and faster way, which is also more resilient. And our second pillar is the impact of technologies and data analytics. And in the past, we also have to support that, we also had a joint symposium with the HDSI, the Data Science Institute at UC San Diego. And our last pillar, which we will have another symposium at the end of June, is the sustainability. And that is the key pillars of our Supply Chain Institute to look at the supply chain of the future. And also for those, for the audience, we have a lot of students. For those students, I will also mention that just stay tuned. We also have a lot of companies hiring, in particular the participating companies in this symposium. So stay tuned. We will give you more information about those hiring opportunities. With that, I want to introduce Dean Pisano. Dean Pisano is the Dean at Jacobs School of Engineering, and also he holds Walter Zabel's Chair in Engineering. He's a highly accomplished mechanical engineer and elected to the National Academy of Engineering for his contributions to the design, fabrication, commercialization, and educational aspects of microelectromechanical system. With that, Dean Pisano.
Thank you, Shin. I appreciate the opportunity and allow me to just make a few brief comments. So first off, I add my welcome to all the other welcomes that you've heard. Let me point out one or two things that I think are really important about this meeting and the future that this meeting will open up. We are at an unprecedented time when, through systems engineering and a bunch of machine learning and other AI tools, technologists and managers are able to have extreme and outsized influence on larger and larger systems and larger groups of people. And with all the changes that are coming to the automotive field, whether it's autonomy or logistic supply chain, we're seeing a natural confluence of technology and people. And so I just want to end my brief opening statement by saying, I think it's spectacular that engineering and Rady are working together on this project. You have my full support. And I'm sorry, I'm just having, whether it's throat problems or computer problems, just having a tough morning this morning. Sorry about that to everybody. But that does not dampen my enthusiasm. And I'm sure that everyone's going to have a great meeting. I'm certainly looking forward to it, and thank you.
What we think is after this COVID, things will change. And one of the key things that we can imagine things will change in that sense will be the automotive industry. And we are not talking just automotive companies, but the whole value chain of the automotive industry. That is really the key focus of this symposium. And with this symposium, I would also mention, like Dean Pisano said, this is really a collaboration between Business School, Rady School of Management, and Jacobs School of Engineering. With that, lots of changes will come. And for the Supply Chain Institute perspective, as I said, we are collaborating with many schools within the university. And also another big important pillar that we are collaborating in this institute is actually our industry partners. And with that, I want to introduce our chair and chair of the advisory board members for the institute, Helen.
Thank you, Dr. Shane. Good morning, faculty and students of UC San Diego, leaders and practitioners from Silicon Valley to Baja California, and the dreamers, technologists, and visionaries of the future. As an industry practitioner, I worked at Apple to launch the first iPhone and witnessed how technology transformed our lives since 2007. Yet, it was hard for me to believe in driverless cars until I joined the Google X in 2013. Today, it's safe to say that the future of transportation will be very different from the past 100 years. It's also safe to say that everyone, including you and me, is part of the upcoming changes in the transportation industry, from disruptive innovation to ecosystem evolution to consumer adaptation. After working for Apple for almost 9 years, I wonder, what's the secret recipe of Apple's long-lasting success? In my opinion, the win-win partnership and the lifelong friendship between Steve Jobs and Tim Cook have made Apple one of the most successful companies in history. Now, I'm working at the intersection of industry and education, and I wonder what it takes to produce more visionaries like Steve Jobs, more supply chain architects like Tim Cook, and more leaders like both of them. We believe ISEI is in a strong position to lead and thrive because ISEI, housed by Rady School of Management, in partnership with Jacobs School of Engineering, and in close collaboration with industry leaders. As the chair of ISEI, I envision a unique approach to achieve our mission. First and foremost, ISEI has a strong board of advisors representing supply chain thought leadership across industries. Many of our board members are with us today. Secondly, we have created experiential learning opportunities for our graduate students through real-world problem solving and industry research projects like PGM. Furthermore, ISEI provides a research and the learning platform to connect industry leaders, academia researchers, and talented students. For example, as Dr. Shing mentioned earlier, our next event is about sustainability later this month. Last but not least, we are building a community and welcome you to join us as a member company, event sponsor, research partner, and many more ways to contribute and support our mission. Together, we will build a better world by developing a roadmap and incubating the next generation of leaders. Thanks again for being with us here today, and please enjoy the rest of the event. Back to you, Dr. Shane.
Thank you very much, Helen. With that, we'll move on to a student presentation.
We set sail on this new sea because there is new knowledge to be gained and new rights to be won, and they must be won and used for the progress of all people. For space science, like nuclear science and all technology, has no conscience of its own.
We find ourselves today in a similar place as mankind found itself back in 1962 when JFK made his famous "We will go to the moon" speech. We are no longer limited by only imagining the future of clean and renewable energies powering autonomous cars. We stand on the precipice of drastic change in the way society moves around this world. Just like in 1962, the next decade will see advances in technologies and cultural shifts in the transportation sector, unlike we have seen in previous decades. Join us as we explore the universe of possibilities today and partner with us as we aim to understand the automotive value supply chain of tomorrow. Good morning, everyone, and welcome to the future of the automobile industry. My name is Dan Peterson, and I'm a second-year MBA student here at the Rady School of Management. Our team has had the immense pleasure of being led by two powerhouses, one from academia, Dr. Hyoduk Shin, and the other one from high-tech industry, Helen Wang. On top of these two, we have had the great honor of conducting exclusive interviews with many industry leaders forging the path into the future. Over the past 10 weeks, I have had the opportunity to work with some of the most unbelievable classmates to discover not only the current state of the automobile industry, but also to explore the future possibilities within that industry. I would like to introduce the team. Noura Al Hashim has come to UC San Diego all the way from the Kingdom of Saudi Arabia with experience in the oil and gas industry. Susan Shang hails from China with experience in the banking industry, weathering the past year in Vancouver with our friendly neighbors to the north. Jeremy Mao is also from China with experience in the finance world and has been in California since achieving his first master's degree from Pepperdine before trading in Malibu for San Diego. Together, we explore the auto industry. Our first stop today will focus on my personal favorite, the traditional automobiles powered by the internal combustion engine. Following that, Noura will explore the alternative energy sources with a focus on battery electric vehicles. Jeremy will then share with us the current and future states of the autonomous technologies. And finally, Susan will walk us through the factors influencing the specific market of shared mobility and wrap up the structure of the future automotive value supply chain. But before we get into everything, let me first walk you through our framework that which we view our research. We call this framework the 5 dimensions, and I will walk you through each one over the next 5 slides. You will see this 5-dimensional analysis in each portion of this presentation that we go through today. The first of these dimensions is hard power. Hard power forces influence behavior through things like policy, infrastructure, and incentives. For example, government regulations play a huge role in determining which technologies will win out in the future. The second of these dimensions is soft power. Soft power forces influence behavior through things like culture. For example, the Toyota production system, focused on just-in-time logistics and lean operations, has heavily influenced how other automakers have approached their assembly line productions. The third dimension is top line. Top line forces deal with revenues. For example, the factors that drive vehicle demand. The fourth dimension is bottom line. Bottom line forces deal with supplier capabilities. For example, manufacturing costs. Finally, the last dimension is time. Industries are kept in balance by the previously listed forces that drive its direction over time. For example, here, the Ford Model T won market share in the early 20th century by its innovative assembly line operations focused on cutting bottom line costs. As much as we all like the Mustang, it was the Ford Taurus that saved Ford from impending bankruptcy in 1985 as top-line demand shifted from boxy American cars to smaller and more fuel-efficient Japanese import styles. Throughout this entire timeline, eras come and go due in part to the hard and soft power shifts that we experience. This first section of our presentation will focus on the internal combustion engine. Society has come a long way since the first modern internal combustion engine was invented by Nicholas Otto in 1876, shown here on the left-hand side of the screen. This technology has grown to some of the most modern internal combustion engines of today, shown on the right, like Infinity's 2-liter variable compression turbocharged engine. There are many factors that brought us from the engine on the left to the engine on the right that powers the automobiles that we know and love today. We view our first factor as hard power. Hard power regulations have aimed to influence consumer and automaker behaviors. The Clean Air Act, passed by Congress in 1970, gave the Environmental Protection Agency the legal authority to regulate pollution from cars by adopting stringent standards. This has resulted in new cars, trucks, and SUVs being 99% cleaner than their 1970 counterparts, according to the EPA. In fact, a substantial jump is evident in just 10 years' time, as demonstrated here. On the left-hand side of the screen, you will see the 2008 Ford F-150, its engine, and its engine specifications. On the right, we see the 2019 counterpart. Over time, companies like Ford have innovated to produce significantly improved engines powering their most fuel-inefficient vehicles through powers like the hard power, like the EPA Clean Air Act. Over a period of 10 years' time, the F-150 has shifted from a normal V6 engine to their EcoBoost twin-turbo V6. The newer engine has drastically slower displacement, which leads to increase in fuel efficiency, as shown by these green boxes and lines. Better yet, both horsepower and torque have increased, as shown by these orange boxes. In regards to soft power forces driving the automotive industry, companies have curbed their investment in new internal combustion engines, essentially only maintaining this powertrain as a bridge into a more environmentally friendly future. Just this year, as demonstrated in this non-exhaustive list, we see spokespeople from companies across the industry reinforcing that they are withdrawing funding from new internal combustion projects and investing heavily in cleaner technologies. These automakers are just a few, and joining the ranks of companies like Toyota and Honda, who have stated their planned exit from the internal combustion market in previous years. Third, let's talk about top-line aspects like sales. Vehicle sales, like all durable goods, are heavily influenced by major macroeconomic events. As you can see on the left-hand graph, over the past 20 years, the light vehicle market experienced a downturn following major economic events. In 2020, light vehicle sales amounted to over 14 million vehicles sold, with 3 out of 4 vehicles being sold as a pickup, minivan, or SUV. Of these, 90% were powered by internal combustion engines running on gasoline, as shown in the pie chart to the right. Finally, we view bottom line factors that reveal how suppliers have organized themselves to increase cost efficiencies. The current state of the supplier market is heavily regionalized. The pie graph on the right-hand side of the screen shows that the top 3 countries to export vehicles into the US. Of these countries, Mexico and Canada make up 50% of all imports. Now, on the left-hand side of the screen, we can see Mexico's vehicle exports to the US have grown steadily since the economic recovery in 2010, with many automakers seeking out investments in the strategic country to nearshore production to the US market. The data shown here and in previous slides demonstrates that while the internal combustion engine-powered automobile still has strong demand today, the lack of investment into new internal combustion technologies and the rise of more affordable, cleaner alternatives have signaled this industry's pending demise. I will now turn it over to Nora to walk us through with a detailed look at the EV industry.
Thank you, Dan. In efforts to reduce pollutants and greenhouse gases, alternatives or renewable energy sources have shown great promise in helping to reduce the number of toxins that are byproducts of energy use, such as ethanol, natural gas, hydrogen, electricity, propane, and biodiesel. Lots of regulations are emerging in North America to achieve these efforts. The table shown on the slide presents different regions and target timelines in North America to achieve 100% zero emissions with the new vehicle sales. Thanks to these regulations, the uses of alternative fuel has increased. The graph on the lower right corner indicates that the use of electric vehicles comes second highest after the flexible fuel vehicles, which are internal combustion engine vehicles, which is why we will deep dive into the electric vehicle industry in just a second. We'll start with the hard power in our 5D analysis. In terms of hard power, emission targets and municipal bans or punitive taxes on users of all combustion engines will drive the growth of the EV. California, as shown on the map at the left side of the screen, has both statutory and executive targets which drove the EV sales to account for more than 3.5% of all vehicles in 2019, compared to 1% and less in other states. As for the infrastructure, the EV to charging station ratio increased from 13.5 in 2016 to 29 in 2021, with California having more than 38,000 charging stations. This indicates a faster growth in the sales of EV compared to the charging stations. However, now with the support of the Biden administration, we will see more growth on the infrastructure side, as they are putting $15 billion investment to fund building a national network of 500,000 charging stations. With clear regulations and policies, innovations in the industry are now more focused. In terms of soft power, the innovation in the industry has been on an upward trajectory. There were 7,000 international patent families related to electricity storage published globally in 2018, with an annual growth of 14% between 2005 and 2018, compared with 3.5 annual growth rate on average for all technology areas. The US has been seeing an increase in filed patents and it's right behind South Asian countries and Europe with more than 870 patents in 2018. The increase in innovation in electricity storage introduced more attractive models to the market that meets the customer's demand and accelerated the adoption of EVs. On the top line dimension, the graph on the left shows the increase of sales of EVs since 2016. The sales in the US increased by 80% in 2018 alone. Moving to the right side graph, the lower operating cost, which includes the cost of fuel and the cost of maintenance, attracts many customers to the EV regardless of the tag price. The increase in sales was also driven by the fact that manufacturers have been competing in introducing high-performing EVs to the market. On the bottom line dimension, with the advancement of technology, Tesla was able to provide the highest miles per kilowatt per hour among all EVs available in the market, which increased its market share. Additionally, on the right side of the screen, we can see the drop of battery prices per kilowatt per hour since 2010. We expect the prices to keep dropping, which will lower the manufacturing and ownership prices in the future. The improvement in the supplier's capability, or in the bottom line, is driven by the improvement in the soft power and will improve the top line in the long run. Now, regardless of the growth that we see in the EV industry, there are challenges that need to be addressed. Based on our research and interviews with the experts in the industry, we highlighted three main challenges. Challenges that are related to batteries, cost, and infrastructure. Starting with batteries, one crucial challenge is that the cell demand growth is outweighing the cell supply. Automakers are now competing for a limited supply of cells. We need to scale up the production, which means we need more raw materials, skilled talent, machines to extract raw materials, factories to process these raw materials. In terms of cost, raw material mining cost is a challenge. Lots of auto manufacturing are investing in battery technologies. However, bringing the whole process locally is costly. Today, battery technology is dominated by lithium and nickel. The issue with lithium is economic shortage, meaning that the lithium prices don't support the mining investment that's required to get it out of the ground profitably. As for the nickel, the challenge is in the refinement process, which is cheaper in Asia than in North America or in Europe. Lastly, in terms of infrastructure, charging station availability and grid capacity is a huge challenge. EV sales continues to increase, but the EV adoption is varying by region, which means that the planning of the charging station demand and upgrading the grid is determined at the local distribution level. Now, given these challenges, we are still seeing and will be seeing more growth in the industry. And with the addition of the future technologies, the transformation of the industry is promising. Now, I will leave you with Jeremy to share with us more details about the autonomous technologies.
Thanks, Nora. For autonomous vehicle, in terms of regulation, the Society of Automotive Engineers defined 6 levels of driving automation ranging from 0 to 5. These levels have been adopted by the US Department of Transportation, and we're currently at level 2. The examples of the current level will be the Tesla Autopilot and Audi Traffic Jam Assist. The autonomous technology has been through 40 years of development. Here are a few milestones that have brought us to where we are today. In 2012, Google Driverless Car project brought autonomous from lab to commercial. In a year since, Google has developed and tested a fleet of cars and initiated campaigns to demonstrate the applications of the technology through, for example, videos highlighting mobility offered to the blind. Later on, Audi and Toyota both unveiled their AV visions in the research programs. During 2014 to 2015, many contemporary car models have features of offering limited autonomous functionality. These include adaptive cruise control, lane assist, and parking assist. From government side, in January 2016, the US government also unveiled new policy which has a commitment of nearly $4 billion over the next 10 years to accelerate the development and adoption of safe vehicle automation. So far, 50 states have introduced the state autonomous vehicle legislations. In regards to soft power, we break down the technological innovation into 3 arrows. The first arrow has already begun, and as we see companies working towards full autonomy for the consumer market, the transition between arrow 1 and arrow 2 should happen in the late 2020s. With consumer beginning to heavily adopt this technology, arrow 3 is where autonomous vehicle become the main means of transportation for consumers. This transition is projected to occur around 2040. On-highway trucks will likely to be the first vehicle to feature the full technology on public roads, as companies are currently developing the software algorithm needed to handle complex driving situations. Based on our research, the autonomous driving market size will grow from $8 billion in 2016 to $26 billion in 2025. According to Bian's survey, safety, lower fuel, and insurance costs were the top reasons many consumers show interest on autonomous vehicles. As good as it sounds, cybersecurity and liabilities are the top concern to many consumers. From supplier side, the B2B market for assistive and autonomous technology, which includes software, hardware, and services sold by suppliers to automakers, promise to be attractive, even in pessimistic scenarios. The number of autonomous vehicles is likely to remain small for the next 5 to 10 years, even in the most receptive markets. But we do see some opportunities from bottom line. Waymo, GM Cruise, and Uber plan to launch commercial services with autonomous vehicle on a controlled basis. Larger scale driverless services are further off, but investors are betting the shift will come sooner rather than later. As we can see from this chart, the market capitalization of the next generation of mobility companies such as Uber and Tesla already have surpassed those of Ford and General Motors. From the bottom line, if we look at the customer cost per mile back in 2019, it is ranging from $0.3 per mile for using public transportation to $3.8 per mile for riding with taxi. Riding hail, car sharing, private vehicle fall between the range. In the future, the customer cost per mile of a robotaxi will be lower than the cost of most other current mobility solutions, ranging from $0.6 to $1.5 per mile. So in the near future, the autonomous technology will bring us to another level of mobility solutions. And I will pass to my colleague Susan to share more insights of shared mobility and how it will impact on our life.
Thank you, Jeremy. We're seeing an increasing number of people moving away from the traditional car ownership model and benefiting from many different other mobility services, including ride sourcing like Uber and Lyft, public transit, including buses and potentially robotaxi in the future, and ride sharing and carpooling, and even the rise of micromobility like scooters. In the past, getting a car symbolized having freedom. While it still does, we're seeing young adults delaying or not even getting driver license. The rate has dropped from 46% to 26% over the last 40 years. While surveying why young adults are not getting licensed, they quote factors include having a car is too expensive, or they're saying that they have capability to travel through other means, such as public transportation and biking. The combined technology development and the cultural shift has increased the role shared mobility plays. In this section, we will look at how the overall value supply chain in the auto industry has evolved. The traditional value supply chain looks like a pyramid shape, where automaker, original equipment manufacturers, OEM, are the kings. There are several tiers of suppliers ranging from raw materials supplier at the bottom, for example, metals, leathers for car seats, component, go up to module suppliers, and fully integrated system suppliers. From our interview with industry expert, we also learned that final assembly for the North American market tend to remain in North America. If you think about it, when you make large products, you want to integrate them close to where they're sold. This can reduce supply chain risk and the cost. Suppliers are developed around US, like Indiana, Mississippi region, and Canada and Mexico. This also has strong regional alliance. As we go further away from final assembly, sourcing becomes more flexible. Companies take advantage of global talent. For example, Asia has strong electronic industry, so it makes sense to source them from Asia. The new value supply chain will no longer be a pyramid. It will look more like a hub where there are different players. Besides the traditional OEMs and different tiers of suppliers, we are seeing big players such as technology companies, infrastructure providers, government, telecom network play a major role in the value supply chain. Without any of them, the wheel will not roll. What we're seeing is that partnership is now new auto industry buzzword. As vehicle becomes more like a technology product, big OEMs are working with big suppliers like Qualcomm, Microsoft, Amazon, Google, bringing new value to the supply chain. One of the potential issues is the clock speed dilemma quoted by KPMG. Different development cycles for different industries. For example, traditional OEM development cycle is around 7 years, while tech and software companies have a much faster cycles. The auto industry must reconcile different rates of change and work together to revolutionize the industry, and we are very excited for the change coming up. I'll pass it to Dan, who will wrap up what we have learned.
Thank you, Susan, Nora, and Jeremy. The future of the automobile has been on the mind of dreamers for decades. Over half a century ago, Batman summoned his car through remote control, with many, many more versions of autonomous cars ever since. Today, cleaner powertrains are just a part of the transformation. The future will be driven by massive innovation that has the potential to completely throw away everything we think we know about how we get from point A to point B. As we move forward into the world, we come with three main findings. First, we will continue to see partnerships between companies with complementary core competencies for the time being until there's more certainty in the technologies that will carry us into the future. Once this occurs, we expect to see substantial consolidation within the industry. Second, the new model of the value supply chain is transitioning from a top-down pyramid approach where OEM is king to one that is shaped like a hub, with new industries adding value to the automobiles in ways non-existent in the past. The different industry development cycles, or the clock speed dilemma, will remain an issue into the future. Finally, while the transition from internal combustion engines to zero-emission vehicles has moved from culturally and technology motivated area to one that is now driven by hard power regulations and mandates, the autonomous transformation is different. The technology is not mature enough for hard power forces to be in the driver's seat just yet. For the time being, autonomous technologies for use on US roadways will continue to be driven by soft power innovation. The next decade will see advances in technologies and cultural shifts in the transportation sector, unlike we have seen in previous decades. Thank you all for participating in our presentation today. We invite you to send your questions using the Q&A function in the Zoom, and we will be answering them within the next couple minutes. Finally, we will now send out a quick poll to gauge your personal views on these emerging technologies during this transition as we transition into the next speaker, and Professor Shin will reveal the responses later in the event. Thank you all for attending our event today.
Great. Thank you very much, Dan. First of all, in the student presentation, as Dan said, if you have any questions, not only in the student presentation, but also in the following panel discussions and keynote speeches, please feel free to use Q&A button in the bottom to ask questions, and then we will answer questions as we go by. And with that, for the next 30 minutes, our speaker will be Benjamin. And Benjamin will talk about from the autonomous technology to the space. So it'll be an interesting talk. And Benjamin leads currently Astra's engineering, manufacturing, launch, and test operations. Before Astra, he spent 2 decades designing and manufacturing hardware at Apple, where he most recently held the role of senior director of the special projects group. With that, Ben.
Thank you, Shin, and thank you to the ISEI for inviting me to chat with you all today. And I'd like to talk with you a little bit about the revolution that's happening right now in robotics, and in particular in autonomous robotics, which is going to fundamentally change, I think, transportation, and not just transportation on the ground, which we talk about, but also in air and space. And to do that, I want to zoom back a little bit in time. I'm one of those folks who actually grew up before we were all heavily using the internet to live our lives. And so I'd like to talk a little bit about what the internet revolution did for us, and then draw some parallels to the robotics revolution. So first of all, real quickly about me, thank you for the introduction. It's been an interesting 2 decades of the last 7 years in autonomous robotics. And then moving over into the space industry, where I've been working on autonomous robots that go to space. So let's talk about the information revolution. Revolutions fundamentally come with big technology changes, which then affect new products, new experiences, create new ecosystems and new markets. And so if you rewind back to 1999, there was this early idea of the digital hub. And so just to frame things a little bit, if you think about what we had on our local computers versus what we had on the internet over in the World Wide Web, for example, our email, the internet was basically for either cruising around websites or transmitting emails from one local machine over the network to another local machine. And all of our music and our video and our games and our work were all located on our computer locally. And what was interesting, in 1999, Apple came out with this computer called the iMac DV, and DV stood for digital video. And it was because there was this inkling in 1999 that that digital video was going to be a thing, and what was going to enable that was the internet was going to get fast enough that downloads would get a lot faster, uploads would get a lot faster, and people would actually want to create digital videos and stream them online to others. And so if you fast forward to today, there's been this huge move where all of these applications enabled fundamentally by this connectivity infrastructure, by broadband, have moved off of local devices and have moved up into the cloud. And so now all your media, all your work, many of our games are all now up in the cloud. And really what we have locally are very kind of custom portals, like physical portals that map to the user application at the time. So for at home or at work or on the go, you have things like a smartphone or CarPlay or Android Auto for a car, for example, and you have your desktop. But these are very kind of bespoke portals into the internet, and then all your information sits in the cloud. And what that has done is really unlocked a whole new economy and ecosystem of applications that nobody could have imagined back in 2006. And if you think about the other piece of it, is that it's all enabled by connectivity. And so you have portals on one side, physical portals on one side, and on the other side, you have all of these services that are enabled for linking us not only to our devices, but also to each other. So if you think about all of the various different services that fundamentally have enabled our social lives to exist in a virtual world and connect folks from literally across the planet, which is a pretty amazing thing. If you think about the robotics revolution and everything that promises, it's this idea that fundamentally we're going to be able to not be driving and instead get that time back to do other things. And that's an amazing promise. And if you think about what that does on land, you can imagine in the air, you don't need pilots anymore. If you imagine in space, you have autonomous vehicles in space. But today's reality looks like this. These are two companies, robotic vehicles that are driving around today. And you can just by staring at it, you don't need to know anything about robotics to know that this requires a tremendous amount of evolution, a tremendous amount of simplification, not just on the AI side, which we'll talk about in a little bit, but in the simplification, in the integration, to get to something that fundamentally can have a supply chain that enables scale. And so let's talk a little bit about what goes into an autonomous robot. The first is a great parallels to a human system because humans are autonomous, right? So the first is that vehicles need sensor systems. Humans use our eyes, we use our ears, we have motion sensing in our inner ear. And so the ability to sense the world around you is really important. The second is you need computation. You need the ability to interpret all of that information in the world, classify it, make predictions about how the world is going to evolve over time, over the next few moments, and make decisions about what you want to do next. And then the way you act on those decisions is through actuators. And so that can be hydrofluidic or mechanical actuators in a vehicle. It can, for humans, obviously, it's our muscles. And then that whole thing is underpinned by a power system. You know, vehicles require engines or require batteries. Spacecraft require batteries. Airplanes require jet engines. Maybe someday the future of airplanes will be electric or hybrid electric. But you need power systems to underpin all of it. There's one more thing, though, which is connectivity. And connectivity is an interesting thing because today it enables humans to work with other humans. For robots, it actually enables them to get much more useful contextual information. So you hear things about like HD maps, for example, that provide all sorts of information for autonomous vehicles on the road about you know, what to expect beyond what their sensors can see. You know, where are the stop signs? Where are the stoplights? You know, where are the lanes? All those kinds of things. However, with robotics, there's something that's more important, or kind of two more factors that are often not considered by humans when they think about their internet connectivity. One is reliability. The way to think about this is, you know, we just all went through, you know, months of working remotely and having our kids go to school remotely. And if you lose, you know, Comcast goes down at your house, the worst thing that happens is your Zoom goes down and you're no longer able to connect to class. Maybe your kids go out and they eat food from the refrigerator they shouldn't have or get distracted, but that's kind of the worst of it. However, with robotics, the loss of that connection fundamentally means that you don't get map tiles. If you've got remote human operation to assist an autonomous robot, be it one that's in the air or in space or on the ground, you lose that connection. You lose any cloud processing. So any functionality that you were trying to offload to the cloud, that's now gone. And so your robot just got a lot dumber. And so if you aren't going to have reliable connectivity, the bar for what your robot needs to be able to do locally is just orders of magnitude higher. In addition, there's availability. And, you know, I experience this every time I live in California. And so every time I try and drive from the San Francisco Bay Area down to LA, where there's like Disneyland and Legoland and stuff like that. And of course, if you drive further south, you get down to UC San Diego. there are all sorts of areas where there just isn't wireless connectivity at all. And of course, my kids complain about not being able to play their videos on their iPad. But imagine that you're a robot relying on all of this information that comes from the cloud, and you now have driven into a dead zone. So that starts to block out places where autonomous vehicle can't even go. And so fundamentally, you need both reliability and availability in order to have a great system. Another example is, imagine you're a farmer and you want to control your farm equipment, but it just so happens there isn't this wireless connectivity in the area where you have your farm. You can't really just pick up your farm and move it. So how do you get great, reliable, and available connectivity everywhere? And actually a connectivity hub in space makes a lot of sense for that, because it's got a really great wide field of view. It's first order resilient to weather. It runs on solar. So once you've got it up there, it runs continuously on renewable energy, which is great. However, there's some major issues with that. One is you need to get it up there in the first place, and then it needs to stay up there and in the right place and pointing in the right direction. And so, in other words, you need the ability to put an autonomous space robot into space, and then it needs to be there. And in order to provide ubiquitous mobility, or sorry, not mobility, but connectivity, it needs to be cheap. It needs to be scalable. And so when I think about that, I go back and I go, okay, well, thinking about Earth and thinking about space, what are the challenges for each? Well, an autonomous robot on Earth obviously needs to be able to read road signs, deal with bad actors, which is a huge AI problem. In space, you have radiation because you don't have the protection of the atmosphere. You have thermals, again, because you don't have the protection of the atmosphere. So there are unique challenges for each. But interestingly enough, there's an incredible amount of overlap, because both need to be able to perceive, both need to be able to decide how to navigate and what they want to do autonomously. Both have actuators that control the position and the pose of the vehicle. They both require power systems, and they both really require highly reliable and highly available connectivity. And so it's amazing to me how much overlap there is. And so to make this autonomous robotics dream a reality, the first is automation, right? There's a ton of work that has to happen in AI and algorithms, and then making those algorithms performant, which means making them really, really efficient. The second is sensors, and a big piece in sensors is really driving to solid state, because with solid state will come reliability, will come scalability. So that's key. Compute. So we've been watching computers become more and more powerful from a computational standpoint while requiring less electrical power. That trend needs to continue. And part of that is designing computers that are really specific to solving the automation kind of problem, as opposed to just general processing. Available and reliable connectivity, we talked about. Power, this is an interesting thing where there's kind of this virtuous cycle going on that was first powered by mobility, driving smartphones and tablets and laptops to have longer and longer battery life and useful video time and call time and internet browsing time, which is really driving batteries to be a lot more efficient. Similarly, the autonomous vehicle industry and the battery electric vehicle industry are driving the power technologies to improve dramatically. Also with renewable energy, that's been driving the solar technologies also to become a lot more efficient versus time. And that's going to enable everything from spacecraft to be a lot smaller and lighter, to things like airplanes, to things like autonomous vehicles. Materials are key, especially when it comes to sustainability. One of the challenges with some of the really high performing materials like carbon fiber is that it's very challenging to recycle them. And so figuring out what the material sets are that are both recyclable as well as highly manufacturable are going to be key. And that's part of why you see a lot more moves towards utilizing aluminum, because it's fundamentally recyclable. You have to build up supply chains in order to enable scale, and that starts with raw materials, as we were talking about earlier in today's talk, through the ability to integrate those raw materials or fabricate those raw materials into parts, integrate those parts into assemblies, and eventually build complete systems. And then lastly, with robotics, because it creates, we're creating a product that actually interacts in the real world. It's not just moving photons of light and making sound by modulating air molecules. It's actually moving around in space. There's a tremendous amount of public and private partnership that is needed in order to make sure that these products deliver tremendous value, but also do it very safely. And, you know, in the autonomous vehicle space on Earth and in the air, you don't want those vehicles behaving badly. In space, you don't want to create space junk, and you don't want to interfere with other vehicles. So you've got to put all these pieces together in order to actually have a complete scalable product and unlock that new economy. So I would like to tell you a little bit about a place that I've been at recently, which is working on autonomous space vehicles. It's called a company called Astra. It's located in the Bay Area. And this photograph is actually of the launch site that Astra has up in Kodiak, Alaska. And part of why I wanted to show this to you is because it's not much. It's power, it's data, it's concrete pad, and it's a fence. And that's not usually the image folks have when they think about launching stuff to space. But this is the vision of Astra, which is really using technology to fundamentally change the story around small satellite launches by really shrinking the entire footprint of what's required. The other thing that's, I think, key about Astra that I found really exciting was that the company is focused on Earth. Astra's not worried about going to space. I care much more about how do I improve life on Earth from space, because I think we're going to be around here for quite some time. And so what do you need in order to put an autonomous vehicle into space? Well, you need the keys to space. You need a launch vehicle that actually can get payloads from the surface of the Earth to space. And so I'd like to show you a cool video that kind of describes a little bit about what it takes to actually get there. So the keys to space, we got there, we got to space, not quite at the velocity we wanted to be at. So we were close. And this summer, we'll actually be launching and delivering our first commercial payload to space. So I'm super, super excited to do that. So then the question is, all right, well, you got the keys to space. Well, that's like kind of getting the keys to the car. It's really like tough. You work really hard to like get your driver's license, you get your car, you get insurance, and you then it's like, well, where are you going to go? And suddenly, like the fact that you have keys and you have a vehicle turned out to be like not the most important thing. And so that's when you start to think about spacecraft. And this has been an area where I've been thinking really hard. And I'd like to talk to you a little bit about what I think the spacecraft of the future really are. The first is that a spacecraft already is an autonomous vehicle. And a rocket, even a multi-stage rocket at the end of the day, is an autonomous vehicle that gets you to space. So why carry two brains to space? You might as well have the spacecraft fly the rocket. I think that makes a lot of logical sense. The second is, and this is partly enabled by the fact that we're really focused on low Earth orbit, the spacecraft of the future are going to heavily leverage the tech from commercial, automotive, and consumer technologies. So we talked about batteries, same story with low power compute, same story with sensors. There's just a tremendous amount of synergy here that I think the industry's waking up to. The next is that it's really going to provide worldwide broadband. It's going to provide that ubiquitous availability, high availability and high reliability connectivity. And it's also going to enable, sensing and Earth observation. And so we're going to learn a lot more about how our Earth works and what our impact on it is. And then hopefully we can learn some solutions out of that that will be very powerful. In addition, there will be IoT. So we'll have connectivity to our infrastructure anywhere and everywhere. And then lastly, I think low Earth orbit is going to be a really big deal. And part of the reason why I think low Earth orbit is a really big deal is not just because of low latency and high bandwidth broadband that comes with being in a low Earth orbit, but also because it allows us to really focus on not leaving space garbage. When you're in low Earth orbit, you're close enough in that you can basically maneuver your satellites such that it will self-deorbit by dragging on the atmosphere when its useful life is over. And that way you're not leaving junk up in space and ending up with kind of like that terrible WALL-E future that we don't want. We want a very clean space future. To do this, though, again, requires scale. Scale is what innovation makes innovation matter. This is a quote from one of my favorite folks to quote, which is Reid Hoffman, who's one of the founders of LinkedIn. And that scale is key because it enables you to have the impact you want. Just showing one of something doesn't actually deliver the impact. One iPhone would not change the world. But thinking about just zooming out and going like, okay, well, what's the recipe for success? Why are companies that innovate sometimes successful and sometimes not? And I think there's a few general rules that are key. The first is seeing around corners, looking at where the market's going to go to, seeing what supply chain we're going to need, seeing what technologies we're going to need, seeing what applications customers don't even know to ask for yet. That's our job. It's the innovator's job. It's to see around the corners and aim to where the puck is going to be. The second is using every tool at your disposal. So globally optimizing, thinking about hardware, software, services, putting all of this together in a way that really delights customers and makes the world a better place. Doing that and solving technical problems, mastering those really critical technologies at a scale that allows for mass production. So it's not just solving that point technology solution, it's solving the whole supply chain problem and integration problem. Is the thing that kind of makes a market difference between a great idea and an impactful great idea. And lastly is velocity. The ability to learn quickly is really important. So, when I think about, the future of transportation, it's really from anywhere to anywhere. And that's from anywhere on Earth to anywhere on Earth. That's from anywhere on Earth to anywhere in space. It's also this theme of, if you look back over the last 20 years of going from mainframe computing to mobile computing and what that means about integration and what it means about simplification, globally optimizing, thinking about what the key enabling technologies are and doubling down on them. And really thinking about platforms. How do we create platforms that enable a new ecosystem? We had no idea that by creating an amazing mobile product and the power of the connectivity of the internet, we'd unlock this entirely new application and connectivity ecosystems. And then lastly, operational efficiency is key. Great ideas need to be backed by great execution. And so if you do those two things, I think you really have a winning recipe. And so I'll just make a shameless pitch for my company really briefly. Astra's hiring. Come join us, astra.com/careers. But really, I'm just looking forward to seeing what, when we unlock this new economy and this new ecosystem through innovation, through a new supply chain, what all the developers and the engineers and the innovators and the supply chain managers and everybody who's involved in like making this real, what they create, because it's really up to them. So with that, I'd just like to say thank you very much for taking the time.
So our next discussion is a panel discussion about electrification in the automotive industry. In particular, we will talk about the discovery of the end-to-end life cycle of electric vehicle batteries and the ecosystem of renewables in electric vehicles. And Dr. Anthony Tong will moderate this panel discussion. And Anthony leads the Energy Storage Integration Lab at University of California, San Diego. He also co-founded Smartsville, a California-based startup focusing on developing low-cost and highly reliable battery second-use solutions. His work is focused on battery energy storage system modeling, management, control, data-driven prognostics and optimization with an emphasis on integration with renewables and electrified transportation. With that, Anthony.
Good morning, everyone, and very glad for the introduction, and I'm honored to hosting this panel for the ISEO discussions. So I think thanks to students' introduction and presentation this morning, and we have seen a lot of the components going into kind of energizing the automotive vehicle sectors. And one of the key components as we coming back to our energy storage unit or battery to be specific in vehicle sectors. And battery are one of the largest components by mass and by cost and function critical components. So as we see more and more as different countries racing to electrify transportations, it become a bottleneck both in supply chain and system integration. So we have a great panel for you guys today, and it's with my honor to introduce our panelists. They are Patrick Kelly from PowerFlex, VP of PowerFlex. PowerFlex are focusing on providing industry-leading solutions for energy management. So he exposed to a wide variety of energy products, including solar, storage, and the integrated charging and the microgrid solutions. We also have Ramesh Bharadwaj. He is a director of battery at Google's. He has ample experience in battery technologies, both with his tenure at the GE and Apple's, now at Google's. He developed many patents in battery technologies and integrated products. Finally, we have Professor Chen Zhen. He is a assistant professor at UC San Diego. His work is focusing on materials of batteries and looking into chemistries and improvement in the battery chemistries to ensure reliability, cycle durability, and the safeties. So as you can see, we are going from product, technology, and the materials. And hopefully today we can have a lively discussion on what this battery supply chain and battery supply chain safety is all about. So again, my name is Anthony Tong. I'm a research scientist at UC San Diego, and I also lead a UC San Diego homebrew startup called Smartsville. So our technology and business model are providing a very interesting perspective of the entire battery supply chain. As you know, we have many electric vehicles being made, and one of the significant components is a battery here. And the battery have a very long supply chain, from minings to materials to cell manufacturing to vehicle manufacturing. So one of the link here we start to see is that battery, after they being retired from the electric vehicle, retains a lot of the capacities, and we could repurpose them for a secondary applications. And that provides significance to the supply chain, because if we can collect, sorting, and utilize them effectively at scale, it also provides a circular channel that could feeding into the industry, a growing industry of battery recycling, and feeding the raw material back to the supply chain of making new batteries. So one of the key pain points we are looking at is how to effectively repurposing and eventually leading to recycle. Of course, different countries have different thoughts based on their labor cost, technology base, and the production scale. So a lot of the solution we see are repurposing them in a lower scale, meaning strip battery downs and all the way to cell module level, or even doing direct recycling. We have seen a bunch of companies doing that. And another solution that we are investigating is if we can use them directly. We call it direct repurpose. So that yields the lowest cost for labor and the cost for integration to the energy storage system. But at the same time, you're giving an opportunity to aggregate retired electric vehicles at large scale. And at the end of their life cycle, we can also sort through them and provide them for a material stream for recycle. So one of the technology solutions we are looking at is to build a distributed hub. Those hubs can be located in anywhere with high EV populations. And we populate those hub facility that interconnect with the grid. And we're providing a collection and the integration platform for multiple EV makers and models. And we can integrate the battery solutions in those hubs to provide the grid energy storage services. At the meantime, we can qualify those batteries based on their performance, reliability, safety, and consistency, and populate a second use product for commercial and industrial business. And at the end of the day, those hubs can be populated to solve one link of the logistic problem and help aggregate large amount of batteries and eventually feeding into the stockpile of battery recycling. So with that, I think it's a good transition to Dr. Chen and talk about his perspective on the industrial battery recycling and his points. Dr. Chen.
Okay, thank you, Antonio, and thank you, everyone. I'm very glad to speak in this symposium. So again, my name is Zheng Cheng. I'm an assistant professor in the nano engineering department and the program of chemical engineering program and material science and engineering program UC San Diego. So I'm going to go very quickly because I was only allowed 2 minutes to quickly introduce the supply chain issues. So I'm putting this first slide showing the long value chain of EV, including batteries, EV manufacturing, and sales and dealership. Okay, so this is normally how we imagine it from materials and engineering perspective. But for normal customers, you will see EVs in dealers, and you will see even in charging stations and running the road. But you want to see the other parts of the supply value chain. Okay, from as an engineer and the scientist, we are interested in how we are going to enable this product and enable high quality EVs and EV services. So the problem is that we are talking about today the value chain, right? How are we going to enable materials to produce this huge amount of electric vehicles and other battery applications, for example, grid energy storage? Okay, so Antonio, do you mind to move to next page? Yeah, so I'm going to put one example. There are a lot of materials used in lithium batteries, particularly high performance lithium batteries. So we have definitely used lithium as the name of for lithium batteries. We're going to use some other precious or critical metals, including cobalt, nickel, and manganese. So I'm putting lithium as an example. So this shows the lithium flow, global lithium flow, basically starting from mining to refining to processing, battery manufacturing, to EV manufacturing, and in the end, to EV customer, to EVs. So I'm not sure if my cursor shows properly. I hope. Oops. Yeah. So so here, if we look at the mining, and then particularly in US, I just want to compare US and Australia and these few South American countries. So majority of lithium are mined is outside the US. So US have almost a negligible amount of lithium mining. Same story, even worse story for cobalt. US does not have any cobalt, basically, yeah, for making batteries. So a lot of lithium as well as cobalt mined from South America or Congo, who has majority 60% of cobalt, will go to China or other Asian countries. Majority will go to China. And then you will see a large fraction of lithium are not going to be used for making batteries. They're going to be used for making glass, making medicines, and making coating material. So maybe only 60% of lithium is going to be used for making batteries. And then most of lithium are still being produced in China. And then this, about more than half of lithium is going to be used in making batteries. And then other countries like Korea, like the United States, taking small portion of the downstream processing and manufacturing, but it's not significant. Okay, so in the end, all this lithium is going to end into batteries, into EV batteries, and the EV is going to be either sold in their home countries or exported in the form of batteries, or in the form of packs, or in the form of EVs to other countries. Okay, so this is a very critical question regarding a few panels or a few audience asked how are we going to have enough lithium to make batteries? So Antonio, if you're going to move to the next page. Yes, so here shows survey of critical materials as going to be demanded or comparing with how much we have in the planet. So actually there are a lot of lithium in the ocean, but this lithium in the ocean cannot be used because their grade is so low and the cost is so high, makes zero economic sense to mine them from ocean. So we have to use lithium from recognized resources. Okay, so so you look at the sea. I'm trying to continue with the lithium story. So in maybe like 15 years, we're going to run out of lithium if we don't have any good solution. Same story, or even worse, of cobalt. In next about 8 to 10 years, we're going to run out of cobalt. And the nickel is similar story. Okay, Tesla is pushing very hard to reducing the amount of cobalt in their batteries. But the same story is that you will use a lot of nickel, and then we're going to run out of nickel in the next 15 years. Okay, so if we don't have any other solution. So one short-term solution is to really enable recycling technology combined with secondary use, which SmartVille is doing. So here we in our lab, we're doing a lot of recycling technology and trying to use the battery, use the EV as a resource to remanufacture new batteries that can reduce or mitigate the risk of critical materials that is significant or heavily demanded in making batteries. So I think that's what I have, and I will be happy to continue discussion after the next two panelists. Thank you.
Yeah, thank you very much, Dr. Chen. And moving on to Ramesh, you want to pull up your slides?
Okay, so I have a short presentation here, 3 or 4 slides. We are just going to talk about the energy densities because that's the important topic. Because everything we talk about battery is the energy density, whether it's a volumetric energy density or a gravimetric. Volumetric energy density is how much energy you can put in a given amount of volume. And the gravimetric energy density is how much energy you can put in terms of weight. So here are some definitions here. So when we talk about volumetric density, which is largely more important for mobile devices, but if you cannot put a lot of energy in a particular volume, then the car battery may be even bigger than the car itself. So volumetric energy density becomes very important. I just gave a very simple calculation. How do you calculate that? So if you have a 5 amp hour cell, you multiply that by a nominal voltage, which is like at a 50% state of charge, and then you calculate the watt hour. In this case is 18.75. Then you calculate X, Y, Z of that particular cell. Take that and convert that into volume in a liter. And then if you divide that number, you will say, this particular battery, which is 5 amps with this size, is 695 watt hour per liter. In the gravimetric calculations, you just do exactly the same thing, watt hour, and then divide by the weight of the cell by kilogram. So those are two important definitions. And then we will talk about cost per kilowatt hour, right? So here is a volumetric energy density roadmap. So in about 2019, we used 4.4 volt chemistry. This is largely relates to the mobile devices batteries, but I'm just defining in such a way can be used same thing in a car industry too, right? So how we are evolving, right? We expect that by about 2024, we will be around 786 watt hour per liter. Today we are about 683. So how much energy you can put in a given amount of volume is increasing consistently. It's not a breakthrough. It's very incremental changes. But I think if you look back like 2007, we used to be around 390 watt hour per liter. Now we are 786. So I think in about 10, 15 years, we have come a long way. Next slide. This is a gravimetric energy density in watt hour per kilogram. So how we are advancing, right? In about 2013, we were at about 154 watt hour per kilogram. I think by 2024, we will be at 400 watt hour. So it's a significant increase, how much amount of energy we can put in a 1 kilogram weight, right? Now we can talk about the cost. So go to the next slide. And now here are the costs. In 2010, it used to be around $1,100 a kilowatt hour. Then in 2013, it came down to $668 a kilowatt hour. Now I think we are in 2020, and then from the cell perspective, it's about $102 a kilowatt hour. But if you make a pack, because we have to put several cells in series and parallel, we are around 137. The projection right now is by 2023, 2024, the range will be somewhere around $58 to $87 a kilowatt hour. When we reach there, the EV car basically will be very in the cost. It will be very similar to the gasoline engine car. And that's where it's going to start making a big difference, because now there's not a cost difference in the cars. So EV probably will take off from there. Right now, the majority of the cost is going in a battery. I think the battery today costs anywhere from $7,000 to $10,000, right? If the watt hour per kilogram, watt hour per kilogram comes down, and by 2024, 2025, we reach anywhere around $70, $75 a kilowatt hour, we compete very heavily with gasoline engine car. So that's where I believe that we will start taking off in terms of EV, because there is no cost difference. There are other things has to come into play. Charging stations, like you have a gas station everywhere, so people don't worry about it. Charging station going to be critical. And I think the range, about 40%, 50% people still bother about the range, how much you can go in a single charge. There will be some technology development in terms of fast charging. If you can charge your battery in like 30 minutes, you will be more comfortable compared to if it takes 8 hours, right? So right now, Tesla car, if you drive 300 miles and you sit somewhere, it might take 4 or 5 hours. There are superchargers, but they are really not still very efficient, right? So those are the things has to happen. But I think battery costs are going down pretty fast, which is very encouraging. So I think I will end it here. Thank you.
Thanks, Ramesh, and thanks for highlighting the importance of supporting infrastructures. I think it's a good segue for Patrick.
What I'd like to show is, first off, that economics I used to think was kind of BS, but it turns out with the grid that supply has to equal demand or else you get a blackout. And it's just a fact of life with the electricity grid. The more demand, you have to meet that, the more you have to provide that with supply. And what that means is that we have a lot of things converging at the same time. California is committing to 100% renewable energy by 2045. That sounds good in theory, but the fact is electrification and integration of renewables is a really hard problem. And you can see year over year, we've had increasing amounts of curtailment in California, and we have increasing amount of congestion at the site of consumption, whether that's inside of suburban areas or cities or at EV charging stations, et cetera. And the point is that renewable production, this is the graph from just yesterday. We were producing roughly 12, 13 gigawatts of solar in California alone. And as you can see, the sun turns out only shines between about 7 a.m. to 7 p.m. in the summertime, even fewer hours during the wintertime. And in order to make all of this work, you have a very intermittent resource with renewable energy production. But the beauty is you have a very flexible demand function with electric vehicle charging. Some of you may be familiar with this curve called the duck curve. And what the duck curve shows is after you take out the demand on the electricity grid in California, when you take that solar curve and invert it and you basically carve it out of that demand curve, you end up with a curve that looks like a duck. It talks like a duck and it walks like a duck. And it's a really hard problem because as the sun begins to shine, you have to ramp down natural gas resources. As the sun begins to set, you have to ramp those natural gas resources back up. Some of that can be solved with a battery, and we're continuing to go down that pathway, but it's not the end all be all. And we have to really start converging towards pushing EV charging into the daytime, in California in particular, right? So when we have 5 million electric vehicles, which in theory, from a nameplate standpoint, if they all plugged into a level 2 charger, it would provide 35 gigawatts of power. That's about twice as much as the entire electricity grid. But from an energy standpoint, it's only about 10% of the overall energy consumption on the California grid. So we really have to be cognizant of how we can incorporate and integrate solar, storage, and EV charging. And you can see that in the project right behind me at our offices in San Diego, where we have 400 kW of solar, 43 EV charging stations, and a battery. And this is actually our load data where we're able to kind of level load all of the energy and the power so that we're not negatively impacting the grid. And ultimately, this turns into this virtual power plant, microgrid distributed assets that allow, if power is needed on one side, we can kind of distribute that, whether that's through V2G, vehicle to grid, vehicle to home, and regular smart charging as well. So I'll stop at that point and thank you.
So let's move on to a few questions that we have for the panelists. So I'll start with the first one. Do you guys think US battery supply chain or lack of it is limiting the EV growth?
I think we have a pretty good, at least Tesla has done extremely well in terms of managing the battery supply within the country. Still they struggle because most of their partnership is Panasonic. There is a cultural problem going on. Japanese basically works very slow. Americans wants to work very fast. And that probably is the issue right now, where the whole gigafactory of Tesla is not working fully because they are extremely careful in terms of safety and reliability and their chain of command, for a small stuff, they have to go and take permission from the, highest level. we want to go very fast, right? And that's why the gigafactory is not working the way it is working right now. But once that gets resolved, I think we will not have an issue of batteries in this country, in my mind.
What about other EV makers moving to, other automakers moving to EV spaces? GM, Ford, do you see their battery supply chain being fulfilled?
Yeah, I don't know the internal story personally myself, how and where they're getting all of that. But, jump in, Patrick or Jang, I don't know the supply chain of other people.
The EV supply chain is getting top priority, and that is impacting stationary storage for sure. The long lead time on stationary storage is pushing out 6 to 12 months. Partly that is raw materials driven, and partly that is standards driven and the integration driven. But it is very clear from my side on the industry that the EVs are taking first priority, and that from a demand, from a consumer standpoint, it's not impacted today, but it certainly feels like it can and will be in the next couple of years.
Yeah, I'm only going to talk about from technology point of view. Yeah, from the survey or calculation from all the past data, we see that a critical material such as lithium is enough to making electric vehicles, but it's not going to be enough for making a great or large scale energy storage. So for now, because the two biggest market, one is in America, right? All these auto companies is going to shift to electrification of the vehicles. This is a trend. It's a good big market. There will be a large investments coming in very soon, as we see from the news. The $100 billion pouring into U.S. market by these 3 Korean companies, right? But the thing is that there's a risk. Okay, no matter how, from technology point of view, there's a risk. The data is over there, and we know how much lithium we have. There's a risk from long term, but for short term, yeah, the performance, the driving range, and the cost still needs to be reduced to the level or similar level of conventional vehicles. Then there will be a huge market ramping up. That's my guess.
Yeah, that's a good point. I think it partially covers one of the Q&A questions. So my next one is, what are the current pain points? As we know, battery have very long supply chain from mining's precursor production and cell production all the way to integrated packs, modules and packs and solutions. So what are the pain points of lithium-ion battery supply chain? Maybe start with Dr. Shen.
The pinpoint, I think there are a lot of pinpoints. Yeah, the resource or supply inhomogeneity or non-uniformity crossing the global market is one of the biggest pinpoint, right? So in countries where they have a lot of lithium and cobalt, such as Bolivia and Congo, they don't have very stable infrastructure. They have a lot of resources, but they don't have a market, or the market is not big enough. And in Europe, in US, and in Asia, some countries, they have a huge market demand, but they don't have resource, okay? So all this transportation and mining process, all this logistics actually consumes a lot of energy and generates CO2 just by shipping things from one country to the other, okay, from one continental to the other. So this is a big issue already, right? So if we want to really minimize the cost of the battery manufacturing process, then the entire manufacturing and supply chain needs to be redesigned, right? And to better accommodate the market demand. This is one thing. The other thing is, to me, I think the pinpoint is how to efficiently use all resources. There are a lot of resources going to make, as I showed in the slides, 40% of lithium is not used in making batteries. For now, people are saying making batteries is probably the top priority in the usage, in the best usage of lithium. Can we replace the steel industry or ceramic industry to do not use so much lithium and save them to make batteries, right? And the third thing is the recycling, right? So there are a lot of recycling companies going on, but recycling for now is not really profitable. Right? And then the quality control and the consistency of batch-to-batch operation in recycling batteries is still a big headache. Right? So there need to be a lot of technology development or improvement to really close the loop for manufacturing, recycling, and remanufacturing.
I think the biggest pain point right now is two I see. The cobalt and lithium prices are going up, right? Battery manufacturing, we are trying to reduce the cost, right? So overall, it's like, it's not balanced, right? We're trying to reduce the cost of the pack and everything else, but lithium and cobalt prices are going up, right? Then there is a copper needed, a lot of copper needed for interconnect and all. Copper prices are skyrocketing, right? And I don't know how to manage that, because if the costs keep going, raw materials keep going up, then the battery cost is not going to come down, right? Although the technology supports it, that we can bring it down. The second biggest point, I think, because it is concentrated at only few places, the raw materials, there is a huge political risk also, right? The world has never been a peaceful place. There are egos problems, and there are various other problems to country. And I see that as a huge risk. And I don't know how this is going to be managed. Then the third thing is we are going to have a problem very similar like what we have in the chip industry right now, because it's not a concerted effort from all sources where you are planning that this is the demand and this is the supply. So we will always be off in demand and supply, right? And then we might end up in a similar situation what we are going through in the chip industry right now. So these are the three things I see.
Thanks. Yeah, but I think in the efforts of secure supply chain, we see a lot of the competing interests, such as mining the fields against mining the urban junks, like AK recycling. Also, competing interest of stationary storage with a mobile electric vehicle using those batteries, and also how we go with critical materials such as cobalt and lithium, and reducing such materials to shorten and reduce the supply chain bottleneck. So my last question will be, what are the enabling technology, as we discussed some of them already, that can potentially strengthen US battery supply chain? Do you see anything in the horizon in terms of manufacturing process, chemistry, and even material strings, new material strings?
In general, I can answer that question. It's like the chemistry can play a very important part. For example, because of the cost of the cobalt, a few years ago, we came up with lithium iron phosphate, because iron is a very cheap material, right? And if cobalt is replaced by iron, it definitely have a lower energy density in general, but the cost should be lower. But the cost of lithium iron phosphate hasn't come down considerably. I think it is an imbalance in supply and demand, because most auto industry people are not using lithium iron phosphate chemistry, and they all want to use lithium cobalt or nickel manganese chemistries. If we start shifting that towards lithium iron phosphate, number one, it's going to be cheaper, right? And then it has a tremendous cycle life. Like it can double the cycle life of batteries. So instead of replacing the battery every 7 years, now it can go for 15 years. And I think 15 years is life of a car. Therefore, car and battery get retired at the same time. You don't have to replace it. My fear is the replacement cost on batteries is going to be huge. China is basically doing very interesting thing like NIO, and they have a swappable batteries, right? And that might be helpful. I don't think we are doing anything like swappable batteries in auto industry, right?
Yeah, should I mention also there are
Replacement.
model being tried out for like ownership of the battery be separated from the ownership of vehicles, things like that.
Yeah, it's like a renting, right? You can rent it or lease it. That will be an interesting concept.
Sorry, the regulations will be the thing that continue to kind of stress the industry, right? And coming back and forth on, those are really the things that we've seen that disrupting very much the here and now of those continuous updates.
Thanks all the panelists for a great discussion. I think that concludes our panel.